Okay, here we go. So I've already written the VHDL for most of this, so it should go nice and quickly. So what I want to do is build up a counter, right? And do it in terms of the SPY device that you guys have already designed, right? So you're trying to update from memory at a given rate. Now, the bad way of doing this, right, is just set load high and let it get to it when it gets there, and it'll run just as fast as it can, right? The better way to do this is program your SPY to be able to have some maximum speed and then tell it to update at the update rate that you desire, right? So you can design the SPY device to go its maximum speed, but then update at a slower rate depending on how fast or slow you want your data to go. Because if you have a sine wave programmed in memory and you want to vary that sine wave's rate, then all you have to do is change the rate at which you tell it to send out those samples, right? And so this doesn't allow us to just sit and have load. So let's build a counter that sends a pulse at a given rate, right? And I didn't program in the generics because I didn't have time. So you'd have to go and kind of manipulate the code itself instead of instantiating with various generics. And we're going to call this just a pulse generator, right? It's a counter that outputs a pulse at a given frequency depending on its count. So let's go ahead and point out a couple of different aspects of this and go through. The only thing that I'm interested in are clock, reset, and pulse. I'm going to do this in a state machine. You don't have to, right? This is just one way to do it. The book has like a million ways to do counter type things, and I'll actually show you one of the book ways in the other one. I have a signal called count. Now I'm going to use unsigned because unsigns are really useful. That's kind of common data type that you'd use on an FPGA, and students tend to shy away from these. And I don't want you to be afraid of them. So unsigned needs a size, right? Because a lot of you have probably run into the problem where you've created something without the 7 down to 0, and it throws you kind of a weird error of like, it cannot be in, what does it say? An indeterminate size or something, or undefined size, something along those lines. All that means is you've missed telling it how many bits to use, and it doesn't know how to make that when it turns into hardware. So you have to use this 7 down to 0. The nice thing is with the unsigned is you're now not using any more memory than you have to, right? Now we don't like to have to deal with writing them all to zeros. Remember that this does not synthesize, but will help me simulate, okay? So the reset is what's going to actually reset it, but this is one way to initialize a vector that has a lot of zeros in it, right? So instead of writing 8 zeros or potentially like 32 zeros, if I had a really big counter, I can just write this others go to 0. I haven't defined anything. I just say the others go to 0. So that will set all 8 bits in this case to 0. I create a signal based off the state type, right? This is an enumerated type. I only need 2 states. It's going to be a really simple state machine. I'm going to process on clock and reset, right? That means an asynchronous reset because the reset doesn't need to be synchronized to the clock. If the reset is triggered, it just happens. This is another way that I can set something to 0. So this is another option to reset a long vector where I just say count, which is going to be what's reset. This is a conversion and is going to convert the integer 0 to an 8-bit unsigned. That's all this is doing, right? So this way, if I needed 32 bits, I would just write that and it would give me 32 zeros. Now, here we're in the rising edge of clock. You guys sometimes forget this rising edge thing, right? This causes problems. Don't forget it. If I'm in state 0, I don't want to create this pulse, right? Because the pulse is going to be the thing that tells the SPY device, for example, to send a data packet. So here I'm just saying it's 0. It is outside of the if because in this state, it is always 0. It's not conditional. I could put it into both of those if statements and it would still be fine, but it's just a little more writing. But if you were to only put it into one, if, for example, if count is less than 20, pulse is 0, and then you left it out of the else, that's wrong because it's pulse is 0, else I don't care, right? Which can cause you problems. And I've actually seen this one cause issues in this particular lab. So make sure that you're assigning it anywhere that you care what it is. If the count is less than 20, then I'm just going to start counting up. This is going to be an up counter, right? A lot of times I do down counters for you guys. So I'm just going to give the opposite example, count up. Because it's an unsigned, I can just add 1. That's allowed. It's fine. Count is not an output, so it doesn't care that it's on the right side of the equation. And it stays in CS. Unless we're greater than, or 20 or greater, right? Then we're just going to go to state 1. We don't need to count anymore. Let's go to state 1. I could reset my counter here if I wanted, but I'm just going to do it down here in state 1. No matter what, I go back to state 0. This just gives me a little bit of time that I spend with the pulse being high. Set the pulse high, and I reset count using this others statement, right? The initial one, just showing that either one of these works, they're okay. That's my pulse generator. This is going to generate a pulse at a rate corresponding to 1/20th the clock speed, right? And I could use this as what's called a clock divider, right? If I needed a clock that is 20 times slower, I could do this. This is also potentially a clock divider, which, there we go. Then the next thing I need to do is I'm going to show you another counter, right? That is really a counter, is all that's doing. This is another counter. Then this job counter is going to count the number of pulses that it receives, right? Which is another function. We haven't used it yet, but you may want to know, for example, how many of something you've gotten, like how many packets have I received, how many whatevers, right? So like, say you were going to build a data acquisition system and you were getting signals back from an ADC. And you wanted to send them in packets over, say, USB, right? Because a USB packet has several, I can't remember the size actually right now, but several hundred kilobytes at least worth of data that one USB packet can save. But you don't want to send more USB packets than you need. So you would just count how many samples that you received, start queuing them up in the register, right? We talked about shift registers a little bit last time. Queue those up, and then once you've counted however many samples you have, then you could send them off over USB. Okay, so this is just going to count how many samples we've sent out. That's all this is going to be doing basically. This counter is pulled from the book, so it's going to be more of the book-centric code, right? I've called it pulse counter. It has a load, a clear, and this is one thing I've changed. I've declared an increment signal. So should I count up or not, basically, and a clock. Now, it has a parallel load, which is all the D is, right? They're flip-flops, things of a parallel load, and the Q out, which is the final output of that counter. There's an internal signal called Q. The reason we do this is it's a counter register that decouples our counter that is on the inside from the output. That's important because here, where I have this increment signal, right? If I want to count up and I write Q is Q plus 1, if this was Q out, that would cause me an error, right? Because I can't put an output on the right-hand side of an assignment statement. So this is preventing that. This internal signal is creating this buffer that allows me to have this kind of feedback situation that we need for a counter. And then we just continuously assign Q out to Q. Okay. Everything else is exactly what you expect. Clear clears it, load loads it. There's nothing fancy. This uses the book version of the rising edge of clock, right? If the clock changes and that change is going to a 1, this is the same function, says rising edge of clock. Then I built a test bench. This test bench does nothing special. It creates a pulse, one instance, or declares the components of the pulse generator, the pulse counter, declares all the signals that I need, And then this here, right, is generating the clock. This is like the easy way of clock generation, just saying clock equals not clock after half a clock period, whatever you need. And for now, I'll show why this matters in a minute, but I'm creating an inverted clock. I create two instances of, or one instance of each of the things that I need, and then I can run my behavioral simulation. So the ideal situation is that I'm making pulses at 1/20th the speed of my clock, and I am counting how many of those happen. Don't forget to hit the zoom to full scale thing, because some of you guys are still running into that problem where you run the simulation and you think it's not working because it's too far zoomed in to start. Don't make that confusion. Also make sure you know how long you're running for and make sure it's relevant. Okay, so let's go ahead and zoom into one of these pulses, right? Because we can see that the pulse, which is the output, that pulse generation is working. Pulse, pulse, pulse. I could zoom in, count to make sure that I'm not off by one because of that less than statement kind of situation, right? That's one of the things to look out for. But let's go ahead and look. I'm going to drag this invert clock out of the way for a minute and drag the reset to the bottom because I'm not doing anything with it. Okay. So we've counted up, and here we have clock. On the rising edge of the clock, we change states from state 0 to state 1 in my counter, right, in my pulse generator. So it goes high. On the next rising edge of the clock, which is here, it goes 0. Now, what you'll notice is that what I'm really looking for, and I should specify this real quick, inside the test bench, what I've done is the pulse TB, that's the output, is just being put into the increment signal, right? I'm treating this like an enable signal, like a counter enable. So it's always seeing the clock, it's just waiting for that enable to come along and say, oh, there is a rising edge of clock and I'm enabled, let's count up, right? So we need to view this pulse TB in two different ways. One, it's the pulse that's being generated to tell it to count, and it is also the enable signal telling the counter to begin, right? So let's look at what that means. This rising edge of clock is the same one that is telling it to go look and see if it is counting up. Should I count up? Well, what do we notice? It does count up, but it is snagging that very end. It doesn't matter how far I zoom in. This rising edge and the falling edge of pulse TB are happening at the same time, right? And that means there's a race condition. It means we don't know if it's actually going to trigger or not, right? Sometimes it will, sometimes it won't. And potentially, if you had the wrong situation, you could have this rising edge trigger it and this rising edge. So I could double count potentially, right? If the leading one jittered forward and the trailing one jittered back, squeeze it in, I'm going to actually count double, which is a big problem because then I'm going to send an invalid data packet to whatever data acquisition system controller I have. So the easy solution to this is if I look at invert clock, which is the one I have at top, and look at this rising edge, which is the falling edge of the main clock, right? It's just flipped, is in the dead center of that pulse. Meaning I can go really fast and it really doesn't matter how bad that jitter gets until I start really pushing the very edges of the capabilities of my system, right? In this case, for your FPGA, it's like 450 megahertz, right? It's not until I get to that point that I'm even a little concerned that I'm going to miss it. This is one of those this is a high speed kind of clock design idea where you want to make sure your rising edge of clock is as far away from any transitions as you can. So all I have to do to fix that is go into the test bench, which in like an application wouldn't be a test bench, right? This would be like your main controller. And instead of using clock TB, which is the main one, I'm just going to use this invert clock as my generator. The reason I'm going to use it for the generator is because I'm going to use the inverted clock for whatever the simplest logic is, right? So I'm going to consider that the main part of my system is running on clock, and these kind of supplementary systems that need to tell it when to trigger is going to be the off clock, right? It's going to be half a period shifted. So I jump in here and set a clock TB. I run invert clock. I can then rerun my simulation. I'm into one of these. I'm now using invert clock. See that falling edge? That's when I count from 0 to 1. I've counted 1 pulse. I have counted in the dead center of that pulse. I have no chance that I'm going to miscount, okay? So this applies to like your SPI, right? So if you're sending this pulse signal to your SPI, just use the pulse signal that generates half a bit period, clock period off of the thing that is telling your SPI when to run, and you will not have to worry about screwing up that system, like missing a data packet. And then you also don't have to deal with the load is always high, which is going to be very difficult when later I make you guys use like variable data rates for your SPIs. Does this make sense to everyone? Okay, wonderful. So now I'm going to switch and talk about the next lab. Right. So you have built yourself a SPI device, right? And that SPI device is pulling things from your memory or from, I'm just going to draw this as an internal module, right? Switches that go into a MUX. Data. Something like that, right? Making choices, which one to do. This is the beginnings of a really simple digital system, right? You can almost start calling this a digital system where the select signal is well, so I've mentioned this before and now's a good time to talk about it, right? Anytime we talk about digital systems, there's really 2 parts to it. There is the data path and there is the controller. The data path is exactly what it sounds like. It's where the data goes. The controller is anything that tells things how to behave. So I'm going to throw in a block that I just talked about, right? That is going to be my pulse generator. That pulse generator goes and plugs into, I guess you guys mostly called it load, that tells the SPI to load this data and begin, right? This pulse generator and this select signal are your controller, right? They aren't data. They're not handling data for you. They're not doing anything. They're telling your data path how to behave, right? And these change on the fly. They configure it. So those orange circles are controller. So our controller gets more and more complicated the more elements of the data path we have. Now, it turns out that the data path gets easier and easier with each lab. So the next thing that I'm going to do is it's going to first start out as kind of like a different digital system, because over here, this is controlling a DAC, right? You're making a signal. Now I want an ADC to record that signal. Okay. So right, I'm getting you guys accustomed to the full scale of digital data acquisition. To interface to that ADC, this is going to come from a Digilant. This was the DA2. This is the AD2. Analog to digital 2. Okay. This guy is actually really slow. He's like a 12-bit, I don't remember. He's not very fast, but it's okay. Makes it a little easier to work with. And the way we talk to the ADC, right? Because this block now is the real world, right? Essentially, this is outside of the FPGA. So the way we need to talk to the outside world here is through this SPI, serial peripheral interface, right? This is just communication protocol. It is one of many, many digital communication protocols. Its benefits are, right, that it's fast. It can talk to many devices without very many wires. But if I wanted to talk to 30 devices, I have the issue that I need one wire for every single device. So even though I don't need 3 or 4 wires for every device, right? Because I need the clock, the data out, and potentially a data in, right? We're not using a data in, but you could imagine one where you have a data in. So clock, data out, data in. Those 3 don't change, those are fixed, and you have one chip select for every device from there on. What if that's too many, right? Let's say that we have a small FPGA. FPGAs often come in the form of what's called a BGA or ball grid array. And what that's going to have is a square IC with little circles on the bottom that have the traces coming out, right? So when physically implemented, if I wanted to go talk to an ADC over here that looks more like that, right, with the little legs, then I would go and I have a trace that comes out and over and plugs in, right? But you can see that I'm limited to some number of IOs. I can't have infinite IOs, so I have to take that into consideration when I'm building a device. So like the seniors that I have working with me on a senior project right now, they use I think every single one of their IOs on their FPGA. And so you have to take that into consideration is, am I going to run out of IOs? So say that I am. Say that I've designed this system and I built a SPI that is controlling 30 DACs. And now I'm going to build, I need an ADC to record 30 DACs, right? That starts scaling up. I need lots and lots of signals. And I realize that, oh, I've already done all this work. I don't want to use the SPI, but now I've got to the ADC. I only have a couple wires left. I only have like 4 wires left for my IOs. SPI isn't going to cut it, right? There is a protocol that works fine. It just is slower, right? That's the game of the trade-offs. Is I can use fewer wires, but it's going to slow me down. Protocol that we're going to use for that trade-off, I2C, I2C. You'll hear it said both ways. It is very similar to SPI in that it has a clock. I'm going to cross over here. So his ports are going to be a clock, which is my input, right? Serial data out, which is my output. This one, well, I'll do it this way, serial data in, right? So I'm going to have a 2-way communication, and I'm done. That's all I need. The reason is, instead of SPI, where I'm using this chip select to drop low and say, I'm ready to begin, I can actually use my data as the chip select, and it goes to all of the devices. But what the devices do, instead of assuming because they've been selected, they record, they just start listening and say, is this my address, right? This is why I started out with this address idea. So we're going to have that same kind of concept as the SPI, right? where we're going to have some header and payload, right? In the case of the SPY, what that header contained was configuration data, meaning how do I want the device to behave? Because like in the case of your DAC, you may be using a battery powered device and you don't always want it on. So you could send a command to your DAC to power down, for example. This case, the header contains more information. And I'm going to call it H0 and H1 and kind of split it into two parts, where the first part is the address. And each of these devices have an address affiliated with them. So when they say that number, right, they're going to have a shift register like we talked about that's going to shift these bits one at a time. And at the end of however many bit address they have, it's going to check and say, is this my address? If it's not, they stop listening. They stop caring to the rest of the payload. If it is their address, then they go look at the header part 1, which is, what do you want me to do? Then the last part is the payload, which is do this, right? This configuration in the payload can work a couple different ways. And let's do it in context of the ADC. So the ADC could receive a power down command, for example. Now, it could have this power down command in the config if I have enough bits and it just powers down. Or, well, let me do this, right? So power down could take a sample. It could, sorry, I'm trying to remember what our other operations are, but let's just stick with these two for now. And so it's going to have configuration. So one way is this is telling it exactly what to do. The other one is, say, I could have just a 1-bit configuration that is either a 0 that tells it to take a sample, right? Just do your normal operation. Or I could tell it to give it a 1, and then the payload, instead of being anything else, is going to have an extra command in it, right? So the payload is just, here's extra data saying this config, how do I treat the payload? Basically is what that is. Could be, right? Now the ADC is interesting because it does need multiple things. You need to send it configuration data, and then it sends you back a sample. Okay? So you might say, hey, device number 3, power down. Device number 2, send me a sample, right? But I have to send 1 packet for each of that. And that's why this is slower, is because it needs that extra overhead of the address every time I say send something to it. So you have a question?
So you said they stop listening after its address is not read?
Yeah.
How do they know when to start listening again?
It waits until certain situation is manifested, which I will talk about in just a minute, because it's device specific. There is another possibility, which if you went through 2700 with me, you'll be familiar with, is instead of SDO and SDI, you may have serial data IO, which is of a type in out. Okay, these in outs are a little bit harder to work with, but they save us another wire. Okay, because I use 1 wire for both the in and the out. Now, we talked about how we do that. Those that had me in 2700 didn't have that benefit because we didn't get that far to the architecture. I drew it for them conceptually, and I will do that now so that we do it. But remember that the FPGA architecture is effectively the same. So say this is the edge of my FPGA into the real world. I have some port. This is going to be an in-out wire. Okay. Well, this is going to be my input, right? It's going to be treated as an input and read things. My output then is going to have an enable signal, right? This is just an enable buffer. If enable is 0, it's not enabled. And what that means is, in this case, it's going to go to high Z, right? And this is a big part of why we want to use standard logic instead of bits, because basically what's happening is I turn off my enable and it disconnects here and it is strictly an input. So what is ever over here can send data in. Because if I have something like, say, an amplifier sending data there, this is driving a signal. And if this is driving a signal, we don't know, right? Dual driven probably shows up as an X. We don't know what it is because it's conflicting. And worse, since you're interfacing to a real world instead of inside of the FPGA, if that conflict, when that conflict happens, it can actually break your FPGA I/O pin because it's trying to source enough voltage from here to make it 0, for example, and this is driving a 1. So if this one's overcurrent protection fails, you break your device, right? Not a good situation. So that's why we use this kind of output enable. This device would have that same kind of thing on it in order for this to work. You don't have to worry about that, right? You professionals designed this AD2 that you're going to interface with, assume that their output enable works, as long as you meet configuration, right? Because it's expecting that your commands are going to be right. Sorry, I don't know what time it is. In practice, the easier way to do this, rather than this, is same thing, right? It's still an output enabled buffer. It's just, it turns out the output enabled buffer is a little bit tricky to write in VHDL, and writing it as a mux, which if I'm not enabled 0, just put a high Z. Ta-da. Now, you may find that, actually, I'm certain you will find, okay, I'm not certain. You'll likely find that you need that other library when you do this lab, right? So I have you delete that first Unisim library. That Unisim library will make this part easier. In fact, I don't remember why, because it's been too long since I've looked at it, but I do recall that you'll need that library in order to make this work and be happy. So I'm pretty sure the lab explains it when we get there. And so let's come back here real quick before I pull up the lab and talk about the I2C interface. So what it's going to do, its main job is going to go through this handshake process that you're controlling, right? Your I2C is a controller for the ADC. Now this gets a little confusing, right? Because it's an ADC controller, but it's part of your data path, okay? The thing that tells the I2C when to run is your controller. So this is where this data path controller thing gets a little confusing, but keep in mind that your I2C is handling data as part of your data path, okay? So it's going to do something like, say, hey, ADC number 1, I'm going to need a sample from you. This is the sampling mode, for example, is probably what I believe is the payload of this. Because there's multiple sampling methods, okay? One of them is single sample. I want you to send me 1 sample from your ADC. If I need to go faster than that, what I say is, I need you to keep sending me signals, data until I tell you to stop, okay? The reason that you would do that is because if it goes into continuous mode, it no longer needs to send the address and the configuration, and your I2C can just sit and wait for 12-bit samples, one after the other, which means that you get payloads faster, right? So that's part of what this configuration is doing, is saying go into a certain sampling mode. Say your sample mode is single, then it's going to reply with its data sample. Now, I have to go back and check because I've switched up this ADC. Sometimes one of the ADCs that I've used in the past has an out and an in, and one of them has an IO. So we'll pull it up and actually look at the one that we're using this time and see, so I can walk you through that data sheet a little bit. But this is what's going to happen, is it's going to send this data sample and then you can process it. But there's a little bit of complication in here because they go through a handshake. A handshake is just confirmation that it got data, right? So what's going to happen is your controller is going to say, hey, I need you to do something. It's going to go, okay, I'm ready for you to tell me. And you tell it. It does it and says, did you get it? And you say, yeah, I got it. Let's move on, right? That's this kind of back and forth handshake that it's going to do. Yeah. That's the brief overview of I2C. And now we can go look at a more specific I2C example in your case. Okay, so if you're curious, you can pull up, well, they're calling it I2S, it's fine. Some of the communication protocols, but what I really want is the files tab in your lab number 4, right? This is going to be your I2C interface. The PMOD 82 is a new thing that we need. I go through and talk a little bit about it here. And then I give you useful links to go look up how to do things. So if I go click on, I really wish this would go away. How do I make you hide? Nope. Floating meeting controls. Yep, there we go. Okay, sweet. I don't know how to make those come back, but I'll figure that out later. Here's escape. Oh, awesome. Thank you guys. I don't use Zoom as much as some do. Okay, so here it is. It's a $20-ish part, not too bad. It's a 12-bit A to D, right? That means it has 2 to the 12 different values that it can record. Those values will be between 0 and VCC, right? There are differential ADs, right? They go from negative half VCC to positive 1/2 VC, for example. You do have those. This one is a 0 to VCC. Okay, single-ended is what that's called. All right, we can go down and look at it, and we can read like the features. It uses an onboard voltage reference of 2.048. Why is that voltage familiar? 2 to the 12, right? That's all that is. So that it's really easy to do that conversion for how much 1 bit difference is. What is the difference between 0000 and 0001, right? Corresponds exactly to 1 millivolt. Okay. This one does not talk about, interestingly, its speed anywhere, right? There is nothing in here about its sample rate. So if we go to the support, it has this reference manual and schematic. The schematic is helpful if you want to see how things are connected. So it has, here's the AD7991. That's the actual part that you're using, right? And then you have like this SCLA, SDA, this is the interface to your FPGA. This is how it's configured. Notice the ground and VCC are ready to be plugged into those PMOD ports, just like your SPI is. Oh, let me turn off the light so it's a little easier to see for you guys. They have these amplifiers that are configured to prevent you from breaking things for your AD. They've done the signal conditioning for you. If you end up taking my sensors class, which is a 5,000-6,000 level, either senior elective or masters, I talk about signal conditioning for ADCs in that. That's one of the topics that we'll go through, but this is just preparing the signal to be recorded. Hopefully designed in such a way to prevent damaging, because ADCs are actually one of the more sensitive devices that you'll ever work with. Because if you go more than even a small amount below 0, for example, it will just break. Because these have to be precision instruments. The more precise something has to be, the more fragile it tends to be. So then you can see that there are 4 VNs because there are 4 ADCs involved in this system. Right? Make sense? Okay. Then we can go back here to the 82 and look at the reference manual, right? We always like the reference manual. It's always going to be helpful. The reference manual is not always useful, but in the case of Digilant, I actually like the reference manuals, and I don't need to necessarily always go right to the data sheet of the device, because this is going to tell you, right, it has a serial clock and it has serial data. Notice here, there is only one serial data. There's no SDI or SDO, it is an SDIO. There's one serial data. Then ground and VCC. So this is a very trace or pin minimal device, which its trade-off is speed. Again, it doesn't tell you how fast it can do things. You can read this, though, that the system boards are able to call a PMOD by sending out the device address of this. Okay, this device has a fixed address. Now, what I want to show you next is going to be the data sheet and why this is the address, because it is actually a little bit selectable, but not for you in this case. You can also see here that the chip can be found by its data sheet. That's where we're going to go find useful information about it. The next exam, I will almost certainly post a data sheet and then ask you questions about designing interfaces to it. Okay. So I also link it here in the lab, so it's pretty easy to find. We can pop over. It comes up. This is just like their overview page. Theirs is going to have kind of the same stuff as the reference manual does. And then if you want the full data sheet, you just click the data sheet button. And here we go. So there are, first thing to look at, it's a 4-channel ADC that may be a 12, 10, or 8-bit. So this data sheet is going to encompass 3 different devices. Make sure you pay attention to which one we're using. Ours is the 12-bit. You can notice things like the temperature range, right? So like this maxes out at 125 degrees C. That's pretty hot. It probably works fine for most applications. Probably doesn't work out too well if you're like putting it next to the engine in a car or something, right? So it might get, if the engine overheats, this device might fail, basically. Things like those are the concerns. Then we can scroll through. We know from here, we're looking for the 7991, which is the 12-bit. This analog devices and linear technology have some of my favorite data sheets, which is why I tend to choose parts from there. They like to give you related devices just in case it's not quite what you're looking for. Then they'll give you the table of contents so you can go look through things. Table of contents used to be more important. Now I can just hit Control F, right, and search for things that I'm looking for. That's usually tend to be what I'm doing, but like here's specification 7991. Most of analog devices PDF data sheets are interactive, which usually means I can just click it and it jumps down to the 7991 specific interactions. And these are a bunch of things that you don't need to know yet. I will talk about them in my sensors class, actually, again, which is like how do we talk about signal to noise, distortion, spurious noise, that kind of thing. These are kind of more advanced topics that are more on the analog side, so won't talk about it here. Resolution just means it has 12 bits, blah, 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 okay? But what you're going to be most interested in, right, because you don't care how this works, because I've done all the work of choosing it for you, what you're going to be carrying out is how do we talk to it, right? And so here, the serial interface, that is the communication that we're going to be looking at, and it's going to have all of this stuff that's talking about how the signal interface works that you probably want to go read. But let's go look at the writing to the AD7991, right? This is the most important page, especially for people that are like me that like to see how something is working in visualization. That's also why I like the state machine diagrams so much, right? Is the diagrams are a visualization of how your system is supposed to work. So this is writing to the AD7991. Now, this data sheet is actually pretty complicated because there's also reading from the 7991, right? Because it's an ADC. The reason that we write is configuration. The reason that we read is to get the samples, okay? So I'm going to show you this one because I'm like, part of me doesn't want to, part of me wants me to make you figure this out on your own, but I am absolutely certain that even with an explanation, you're going to be confused as can be. So let's go ahead and do it. There are only two signals that we care about, clock and serial data. Now, this start by master condition is tricky, and I'm going to explain it to you, and then you're going to have to read it at least 6 more times before it settles in. That explanation is somewhere up here, and this is actually a really good data sheet. So is this reads? The start condition is probably described in the previous one. Oh, I am recording my screen, so I should probably just do it from here. Well, here what I'm talking about. Start condition. There we go. Here's a diagram of your start condition. How easy does this look? Right? This is how, going back to the question earlier of how does it know when to start? It knows when to start because your clock is high, your start condition is high, and then drops low here. It needs to have a certain fall condition. You don't have to worry about that there. The falling edge is here, and then it's going to have a rising edge on the clock. Now, I'm sure they do this in Word somewhere. Here you go. Master start by establishing a start condition defined as a high to low transition on the serial data line while the serial clock line remains high. So if your clock is currently high and you drop data, that's your start condition. Okay. That's how it knows when to start looking for an address. There is also a stop condition that I'll let you figure out on your own because it's also in words and is very similar. Okay, now there's that start condition. Now we're going to have a rising edge of clock, right? That's going to start reading in data. We can see these rising edge of clocks need to meet certain conditions. Let's see, what else do I need to point out? Here's going to be something like your configuration header, right? Which is the serial bus address byte, 8 bits of address, okay? Then it's going to have this command of read or write. Which one is it? Which it's 1 bit, so that 1 is read, write is 0, right? That's why that bar is over the W. It's 1 bit to tell it whether I'm reading or writing. Then it goes into acknowledge by ADC. This is the ADC saying, yep, got it. Okay. Notice that this is writing onto this serial data line. And then for 1 clock cycle, you have to go into read mode. Right? Same line. So you have to turn off the enable of the mux to allow data to come in. So you write, disable your output, read the input, and then go back writing. Well, actually, in this case, if I'm in the read mode, write, read more. If I'm in write mode, send the byte, tell it to read, or tell it we're writing, and then send a configuration register byte. And then stop, right? Write is do this one thing and then stop. Read is, here's the address, tell it to read, do the byte read, and this is where it gets confusing, okay? This one is a little confusing for students, is that we have an acknowledge by the master in the middle of this, right? Because it's a 12-bit ADC, but it's going to send 2 bytes, right? So it's always going to go 0, 0, channel ID, right? Because there are 4 channels. There are 4 ones. It's going to say this is where the channel is coming from, which you choose by setting up with configuration, right? Then it sends the first 4 data bits. Then the master says, yep, I'm good, keep going. If you fail to send that acknowledge, the ADC will bail out and stop. So you have to send the address, the ADC acknowledges, sends you data, you acknowledge, and then it sends you the next byte, right? The 8 lower bits. Then you do this. This is also no acknowledge by the master. What that means is if I don't acknowledge it, I can then stop. If I send an acknowledge, you're gonna have to read the data sheet to fully get this, but if I send an acknowledge, it will just send, it can just send me another sample, which is confusing, right? Acknowledge is, okay, we're done. If it's got it, it will go, okay, and you want another one? Here it is. Okay, so this is why the data, being able to read data sheets is important. And I'm introducing you to an easy level, which is just this data interface, is because all devices are always just a little bit different. And assuming that you know what it is without reading it is going to get you into trouble. So again, read is send the address, tell it to read, it will acknowledge, you'll take the bit, you'll acknowledge, it'll send you the remaining bit, you'll stop. Okay. Now there's a new concept that I want to introduce here, which I've mentioned before. I guess it's not introduced, reintroduce, right? Is overhead. If I could ask you what percentage of this interaction is overhead?
Would that be the header and the address and all that stuff? That's not part of the data.
Yes, yeah, it's the ratio of stuff that isn't the data. Is what is the percentage of not data to the total size of the packet, right? That's what overhead means, is how much overhead does it take in order to make this communication protocol work? There is a lot more overhead for this than there is for SPI, right? Because SPI can be very simple. There's no address. In fact, you can imagine SPI where there's no even configuration. You could have a no overhead SPI realistically. You can't have no overhead I2C.
Is the I2C clock just a regular clock, or is it kind of like a SPI clock?
It's going to be high until activated because of you want it to be high for your start condition, right? So you're going to put it into a situation where it can be started. Your stop condition is kind of the same thing, which is going to be like a rising edge of clock while the clock is high, I think, but I want you guys to go read and verify that that works. Again, you're going to want to start this whole thing by writing a state machine diagram of how this works, taking into account, and my recommendation, you're going to kind of need two, right? There's one situation where you're going to have to set up its configuration, which is to say, how do you want me to work is the ADC's question. And then you need one that actually reads the data. Okay. Bounce up to the table of contents, and we can go and look through. This is one that pin configuration and function descriptions. Now, here's the overall pin. Here is how you might have more than one of them connected. So the 7991 has two different part numbers. There's a 7991-0 and a 799-1, and they have different addresses. So I could set two of these up on one SPI interface. I couldn't do a third because I don't have a third address. A different way that these configuration, some of these won't have multiple part numbers. What they'll do instead is add extra pins that are address configuration pins, where you either pull them up or pull them down, right? 1 or 0, and that will configure what its address is. That's another kind of common option. So this one, I don't remember what part number you'll get. And I think there's a couple that actually have a different -1 or -0. So you actually have to look at your part and see if you have a -1 or a -0 to determine which one of these is your address, right? Let's see, is there anything else I wanted to talk about here? So we have your address, you have the pin configurations. Yeah, okay. Let's go back and look at the lab and see if there's anything else that jumps out of me. It says to draw a block diagram for it, do the interface in the controller. Talks about you're going to need an in-out port, which is going to be declared as an in-out. You may have to do a little reading if you're not familiar. Here's where you're going to get tricky, is this sentence right here. You will need a top-level module that provides interface to the I2C and displays the 6 most significant bits from the ADC to the onboard LEDs, so that I can quickly look at your FPGA and make sure that you're getting at least close to the right value, right? Just like I had you use the bigger MSBs of the SPI to set with the switches. This is just the reverse of that, right? Because the SPI is set it with the switches. The I2C is show me what you got, right, on the LEDs. And you're going to have, at the push of a button, one of those push buttons on your thing, which probably needs some debounce, right? So you're going to push a button and it's going to store 1 second of samples into block memory. So you've now done read-only memory. Now you need RAM. So you can have a block memory to read and a block memory to write into. Okay. Make a test bench, and I would make it without the block memory first, for sure, because it adds complexity, right? And it's good enough to just see the lights and make sure it's working, and then try and store it into the memory later. And then there's a whole bunch of stuff that of how you get your points. So hopefully you guys spend time before lab, which is Wednesday, getting finished with your block memory. I do intend, if I pull up the schedule here, we're at lab 4, plugging through the semester. We've passed the halfway point, which is pretty cool. Here, this floating point representation and the functions attributes, I've already talked about functions and attributes, right? Way back when with the tick, like tick event and tick size and all of that stuff. So this one actually is short. So hopefully on Wednesday, you will get some extra lab time. So which will actually be helpful, right? Because we'll do lab in the morning, you'll get a little of a break and then come back to lab. So that normal brain sluggishness that starts because it's been a while since you've done it, hopefully will get out of your system Wednesday morning. And then I have more lab time the following one, because this lab is going to kick your butts. I have no doubt of that. I may have to eat into one of the other of these lab times simply because I still haven't talked about multipliers, which isn't critical, but it is very fun. And then we're going to start, maybe, I'm really going to try to change this up a little bit. These next 5 lectures, we don't actually build into a project. There's some homework around it, but it's kind of an introduction to microprocessor architecture, which kind of helps lead into 3710. If you've already taken 3710 or in it now, it's probably trivial. I don't go too much into depth because it's better suited for 3710. And so, and MIPS itself, which is what's in this book, is kind of an older architecture itself anyways, but it kind of help you orient yourselves in the process. Anyways, these 5, I'm not entirely sure that they'll be the same. That I do want them changed. I just have to make sure, try and find the time between now and then. But the pipelining will stay the same. We have to talk about pipelining for sure. Anyways, that's a look at what we're doing. This hopefully helps you guys prepare for the next lab. And keep in mind that you should use generics, since I've taught them anywhere that you have something that could vary. For example, sample rate, right? When you use the counter to calculate your sample rate, which you can determine your maximum sample rate, again, from the 87991, which is going to find, and I don't actually have time because it's the end of class, but basically what you're gonna have to do is go find its maximum clock speed and then figure out how fast you can pull data out based on that clock speed, which I believe is an exact exam question that I did last semester, where I gave them a data sheet like this that doesn't explicitly state its maximum clock speed. And instead you have to figure out how fast it runs. All right, end of class. I'll post this video so that you guys can come back and look at it when you're inevitably confused, but hopefully it works out.